What if everything you were taught
10,
about limits
9,
was only the
8,
beginning?
7,
From the moment we first
5,
looked up
we have
at the
to go
night
reading
sky,
start. 2,
we were told
1,
there is one ultimate
0,
boundary
booster
written
ignition,
into the
and
fabric of
liftoff
reality,
of Shuttle Endeavour with
the speed
NASA's
of
final
light.
space station crew
Nearly
compartment that brings a bay
300,000
window view
kilometers
to
per
our
second,
celestial backyard.
untouchable, unbreakable, the universal speed limit defined by the genius of Albert Einstein. Nothing with mass can cross it, nothing can outrun it. That is the rule. But tonight, I want you to question the rule, because the universe is far stranger than it appears. Particles can whisper to each other across unimaginable distances. Space itself can stretch faster than light. Equations hint at bending reality instead of racing through it. And beyond all of that, there is something even more powerful. Something inside you. In the next few minutes, we are not just going to talk about physics. We are going to challenge the very idea of limits. We will explore what truly moves faster than light, what science allows, what it forbids, and what it secretly inspires. So stay with me, don't blink, don't drift, because by the end of this journey, you may never look at the speed of light or your own potential the same way again. The idea that the speed of light is the ultimate cosmic limit comes from the revolutionary work of Albert Einstein, and his theory presented in relativity, the special and the general theory. In special relativity, Einstein showed that the speed of light in a vacuum, approximately 299,792 kilometers per second, is constant for all observers, regardless of their motion. This was shocking because classical physics assumed speeds could simply add together. Einstein proved that space and time themselves adjust in order to keep light's speed unchanged. As an object moves faster, time for it slows down and its length contracts relative to a stationary observer. As it approaches the speed of light, its mass effectively increases, requiring more and more energy to continue accelerating. To actually reach light speed, an object with mass would require infinite energy, which makes it physically impossible according to our current understanding of physics. This limit is not just about motion, it protects causality, ensuring that cause comes before effect in every frame of reference. If information or matter could travel faster than light, it could create paradoxes where events happen before their causes. The speed of light, therefore, acts as a fundamental boundary built into space-time itself, shaping how energy, matter, and information interact across the universe, and defining the structure of reality at the deepest level. Quantum entanglement is one of the most mysterious and powerful predictions of quantum mechanics, deeply connected to the work of Albert Einstein, and later formalized through experiments inspired by John Stuart Bell's theorem. Entanglement occurs when two or more particles interact in such a way that their quantum states become linked. After this interaction, even if the particles are separated by vast distances, across cities, planets, or even galaxies, the measurement of one particle instantly determines the state of the other. For example, if two entangled particles are created with opposite spins, measuring the spin of one immediately tells you the spin of the other, no matter how far apart they are. Einstein famously referred to this as spooky action at a distance, because it seemed to challenge the cosmic speed limit established by relativity. However, entanglement does not allow usable information to travel faster than light. The outcomes are fundamentally random, and only when results are compared through classical communication, limited by light speed, does the correlation become clear. Experiments conducted over decades have repeatedly confirmed that entangled particles violate classical expectations and follow the predictions of quantum theory. Entanglement reveals that reality at the quantum level is deeply interconnected, suggesting that particles do not possess definite properties independently of observation. Instead, their properties exist in a shared quantum system, redefining how we understand separation, locality, and the structure of physical reality itself. The idea that space-time itself can expand faster than light comes from observations made by Edwin Hubble in the 1920s, when he discovered that distant galaxies are moving away from us, and that the farther they are, the faster they recede. This discovery provided strong evidence that the universe is expanding. Importantly, galaxies are not simply flying through space away from one another like shrapnel from an explosion. Instead, space itself is stretching. According to general relativity, space and time form a dynamic fabric that can curve and evolve. When cosmologists describe galaxies receding faster than the speed of light, they are not violating Einstein's cosmic speed limit because the galaxies are not travelling through space at superluminal speeds. Rather, the metric that defines distance between points in space-time is changing. Over extremely large cosmic scales, this expansion can cause the distance between two galaxies to increase faster than light could travel across that distance. This phenomenon is especially significant in the early universe during a period known as cosmic inflation, when space-time expanded exponentially in a fraction of a second. Even today, very distant galaxies are receding from us at effective speeds greater than light due to ongoing expansion. This does not break relativity because special relativity limits motion through space, not the expansion of space itself. The expansion of space-time reshapes our understanding of distance, motion, and the large-scale structure of the universe. The concept of warp theory emerges from solutions to the field equations of general relativity, first formulated by Albert Einstein. Instead of attempting to accelerate a spacecraft to speeds approaching light, which would require enormous and ultimately unattainable amounts of energy, warp theory proposes manipulating spacetime itself. In 1994, physicist Miguel Alcubierre introduced a mathematical model now known as the Alcubierre drive. His solution showed that it is theoretically possible to contract spacetime in front of a spacecraft and expand it behind, effectively creating a warp bubble. Inside this bubble, the spacecraft would remain locally stationary and would not exceed the speed of light in its immediate region of spacetime. However, because the space around it is being reshaped, the bubble itself could move faster than light relative to distant observers. This idea does not technically violate special relativity, since nothing inside the bubble is travelling through space faster than light. Instead, space itself is doing the moving. The challenge lies in the requirement of exotic matter with negative energy density to stabilize such a bubble. While quantum effects like the Casimir effect hint that negative energy may exist in small quantities, producing and controlling it at the scale required for interstellar travel remains far beyond current technological capabilities. Warp theory remains speculative, but it demonstrates that the equations of general relativity allow surprising possibilities when space-time geometry is treated as something that can be engineered rather than merely observed. The distinction between information and physical travel is central to understanding why faster-than-light phenomena remain so constrained in modern physics. According to special relativity, no object with mass and no usable signal can travel faster than light without violating causality. This means that cause must always precede effect in every frame of reference. However, quantum mechanics introduces correlations that appear instantaneous, especially in the case of entangled particles. When two particles share an entangled state, measuring one immediately determines the state of the other, even if they are separated by vast distances. At first glance, this seems to suggest that information has travelled faster than light. Yet the key detail is that the measurement outcomes are fundamentally random. An observer cannot control the result of a quantum measurement in a way that would encode a deliberate message. Only when both observers later compare their data using classical communication, which is limited by the speed of light, do the correlations become meaningful. This principle is formalized in what physicists call the no-communication theorem, which proves that quantum entanglement cannot be used to send usable information instantaneously. Physical travel involves energy and momentum moving through spacetime, while information transfer requires controllable signals that can encode messages. Even though quantum systems reveal deep non-local connections, they do not permit faster-than-light signaling. This preserves the consistency of relativity, while allowing quantum mechanics to display correlations that challenge classical intuitions about separation and locality. The idea that human thought and imagination can outpace light is not a physical claim, but a profound reflection on the nature of consciousness and cognition. Light, travelling at nearly 300,000 kilometers per second, requires measurable time to cross cosmic distances. It takes more than 8 minutes for sunlight to reach Earth and years for starlight from nearby systems. Yet the human mind can instantly picture the surface of Mars, the rings of Saturn, or galaxies billions of light-years away, without waiting for photons to make the journey. This mental leap is possible because thought operates through neural processes that encode memory, perception, and imagination in patterns of electrical and chemical activity within the brain. While these signals themselves are bound by biological speeds far slower than light, the conceptual act of imagining distant places or future possibilities feels immediate because it is not constrained by physical distance in the external universe. The brain constructs internal models of reality, allowing us to simulate scenarios, revisit the past, and project into the future within fractions of a second. This capacity has driven every major scientific and technological breakthrough. Before spacecraft travelled beyond Earth, someone imagined them. Before equations described space-time, someone conceived the possibility that space and time were linked. Imagination does not violate relativity. It transcends limitation symbolically rather than physically. It represents the ability of consciousness to explore realms beyond direct sensory reach, demonstrating that while matter obeys cosmic speed limits, creativity and vision operate in a conceptual domain. Where distance and delay lose their ordinary meaning, light is extraordinary. It defines the structure of space and time, sets the ultimate speed limit of the cosmos, and protects the order of cause and effect. From the equations of Albert Einstein to the strange predictions of quantum mechanics, we have learned that the universe is both disciplined and mysterious. Nothing with mass can outrun light. Space-time itself can stretch beyond it. Entanglement can link particles across unimaginable distances, and theoretical ideas like warp geometry challenge the boundaries of what we think is possible. Yet through all of this, one truth stands out clearly. Progress has never begun with speed. It has begun with imagination. Every discovery started as a thought. Every breakthrough was once an idea that refused to accept limits. The universe may set boundaries for matter and energy, but it has never placed limits on curiosity, courage, or vision. When you dare to think beyond what seems possible, you step into the same tradition that reshaped physics and expanded humanity's understanding of reality. So as you move forward, remember this: the speed of light may define the cosmos, but your determination defines your journey. Keep questioning, keep imagining, keep pushing beyond what is comfortable or familiar. The next great leap in science or in life will belong to those who refuse to be confined by today's limits. Thank you for your time, your attention, and your curiosity. I wish you bold ideas, fearless thinking, and the courage to chase visions that seem faster than light. Good luck on your journey. The universe is waiting.